1.6, other types of equations and applications. So we're going to start with rational equations. Remember when we spoke of rational expressions, that was where you had basically a polynomial over another polynomial. So we're dealing with rational equations, should be a line on that T, then you're talking about an equation that involves at least one rational expression, such as x plus 1 over 3 minus x squared is equal to x over 3x minus 2, or something of that sort, right? So that would be a rational equation because it includes rational expressions. When dealing with a rational equation, we want to come up with what are called proposed solutions. And proposed solutions are values that appear to be the solution once we have multiplied through this whole equation by a common denominator. If we multiply this whole equation by a common denominator, we essentially wipe out the fractions and get it to something simpler that we can work with. Now, the only problem with these proposed solutions is that when we find a common denominator for this and we multiply it through, we now have eliminated these denominators, which this one has a value for x that cannot be part of the solution set. Any proposed solution that would make one of the denominators in the original equation be equal to 0, we have to eliminate, we throw it out. So the process for solving something like this, we're not going to solve this one. This one was thrown up here randomly and I don't want to deal with that. But the process for solving these would be find the common denominator, multiply through by that common denominator, then solve using methods that we've already dealt with. If it turns out to be a linear equation, then solve it using the linear methods. A quadratic equation, solve it as such, etc. So let's take an example here. 2x minus 3 over 2 plus 5x over x plus 1 is equal to x. So we have a rational equation, rational expression. That one doesn't have a denominator, but that's okay. So basically what we're saying is, if we're going to solve this, what we want to do is get rid of the denominators. And the easiest way to do that is look at all your denominators. I'm just going to put a 1 under here because obviously x is equal to x over 1. And I'm going to look for the least common denominator. In this case, 2 times x plus 1 would be the common denominator. It's the least common denominator. So essentially what we're going to do is we're just going to take this and multiply it through this. And obviously as we do that, that's going to end up canceling out. The denominators are there. So what I'm going to do is, as I do, I'm really going to cancel out the part that cancels out each time to save myself a little effort. So I go 2 times x plus 1. Well, the 2's already here, so I'm just going to multiply this by the x plus 1 and cancel out that 2. So I'm going to have x plus 1 times 2x minus 3. You could say that I multiplied it by 2, but then I just canceled that 2. So that's why I didn't write it down. I could leave it as 2 over 2, but I'm just going to cancel that anyway. So why bother writing that down? I'm going to get my 2x plus 1 off to the side here. 2 times x plus 1, just so it's not in the way here. Plus, well, this one, if I multiply it by x plus 1, that's going to cancel out. If I multiply by the 2, 2 times 5 is 10, so I'm going to get 10x and then is equal to, well, here I have to multiply by 2x plus 1 times x, so I have 2 times x plus 1 times x. And now you can see I eliminated the denominators. Another way that people look at this is they just find the common denominator and work through, and then they just can wipe out the whole thing. So let me just quickly show you what I'm talking about here. Basically, I can say, well, the common denominator is 2 times x plus 1. So I multiply this by x plus 1. Right? And this by x plus 1. So you multiply the top and bottom by x plus 1 there. I multiply this by 2 on the top and 2 on the bottom. And I multiply this one by 2 times x plus 1 and 2 times x plus 1. And by doing that, I have 2 times x plus 1 in the bottom of each of these, and you can just cancel those all out. They just disappear. Because if I were to multiply the top by, or multiply through by 2 times x plus 1, it would just wipe all that out. So the red was showing another method that people may use to kind of abbreviate or simplify the process or make it a little quicker. So I'm just trying to take out the red, still leave the original stuff here. It's a little sloppy dealing with that. So there you go, close enough. So now we can see it again. So we got to this point, and now I'm going to multiply through, combine like terms. So I have x plus 1 times 2x minus 3. Using FOIL, we get 2x squared minus 3x plus 2x minus 3 plus 10x is equal to, well, I can call 2 times x 2x. So I'm just going to multiply that through. 2x times x is 2x squared. 2x times 1 is 2x. Now I'm going to get them all on the same side. So if I move 2x, subtract 2x squared from both sides, that cancels out. If I subtract 2x from both sides, I have minus 3x plus 2x minus 2x, which gives me minus 3x. And then I've got another x there. Let's combine it first, just so we don't do anything foolish here. Combine like terms on the one side before we start moving things around. So I'm just going to do that. 2x squared minus 3x plus 2x is minus x, plus 10x is plus 9x. So plus 9x minus 3 is equal to 2x squared plus 2x. Just to make it cleaner. Subtract 2x from both sides, cancels out. Sorry, subtract 2x squared from both sides, cancels out. Subtract 2x from both sides, and you have 7x minus 3 is equal to 0. Now that we have that, we can solve for x. So add 3 to both sides. 7x is equal to 3. And then divide both sides by 7. X is equal to 3/7. And then we want to make sure that this doesn't make any of the denominators 0. And obviously our denominator x plus 1, 3/7 is not going to make that 0. So that's a proposed solution, and that's a verified solution that it doesn't make it 0. To go back and actually verify to make sure it actually works, we'd have to plug it in all these places. And to be honest, I'm not going to take the time. You can do that, and you can verify that on your own. Let's try another one. X over x minus 5 plus 5 is equal to 5 over x minus 5. Okay, so we've got our rational equation here, and we look and say, well, obviously x minus 5 is the common denominator we want to deal with. So I really only have to change that one. So I have x over x minus 5 plus 5 times x minus 5 over x plus minus 5 is equal to 5 over x minus 5. We can cancel out all those denominators just by multiplying through by x minus 5 in each term, leaving us with x plus 5 times x plus 5 is 5x minus 25 is equal to 5. So I have x plus 5x is equal to 6x minus 25. Well, I'm actually going to move that over to the other side, just add 25 to both sides, is equal to 30. 25 plus 5 is 30. Then divide both sides by 6. X is equal to 5. So we have a proposed solution. So now we're going to take that proposed solution. We're going to look up here and see what happens. Well, if I take 5 minus 5, I get 0. We can't allow it to divide by 0, so that is not a valid solution. Therefore, the solution set for this problem is the null set. There is no solution to this problem. But a good example, relatively simple, shows that we sometimes get in a proposed solution that does not work. And why did that happen? Because when we are dealing with this, once we've multiplied through by that x minus 5 and got rid of the denominator, then we got into this linear equation that was solvable and didn't have any restrictions on it. But we have to remember that we have to make sure that we don't come up with a solution that violates the original equation. Even though these equations are equivalent, we did things that kept them equivalent. We multiplied the top and bottom of a rational expression by the same number, basically multiplying by 1. That doesn't change the equation, supposedly. It gives us an equivalent equation. We then multiplied both sides by x minus 5, went all the way through. That didn't change the equation, but it did. It gave us an equivalent equation. But by doing that, it put us into a situation where we could get a solution that did not work for the initial equation. You always have to go back and compare against that. I think I have another one here I want to look at. X minus 5 over x minus 3 plus 1 over x is equal to negative 7 over x squared minus 3x. Okay, so again, we have our rational equation here. And if we're looking at this, we go, well, we want to see what's the least common denominator. I see x minus 3, x, and this x squared minus 3x. You may recognize that if you factor that, you get x times x minus 3. So essentially, that is just the product of these two. So all I need to do is go through and multiply this by x and this by x minus 3. So I'm going to do that. And, well, I'll do that first. So we need to multiply this by x. So we have x times x minus 5 over x times x minus 3. Plus, we're going to multiply this by x minus 3. X minus 3 times x over x times x minus 3 is equal to negative 7 over x times x minus 3. And now that whole denominator can disappear. Once we've got it over a common denominator, that's gone because it's eliminated just by multiplying through by that common denominator. So as I bring this down, I'm going to do the multiplication. X times x minus 5 is x squared minus 5x plus x minus 3 is equal to negative 7. So I'm going to combine like terms here. So I have x squared minus 5x plus x gives me minus 4x. And then I have minus 3, and I have a negative 7 over here. I'm going to add 7 to both sides. So minus 3 plus 7 gives me positive 4 is equal to 0. Okay, so now I have a quadratic. We can work with quadratics, and we could use the quadratic formula for this, but I hope that you notice leading coefficient of 1 usually puts us in the direction of let's see if we can do it by using the zero product property first, as opposed to using the quadratic formula. So we're looking for two numbers that multiply to positive 4 and add to negative 4. Now I'd hope that you would see that as negative 2 and negative 2. Negative 2 times negative 2 is positive 4. Negative 2 plus negative 2 is negative 4. So we can say that's x minus 2 is equal to 0. So we can set those equal to 0, which we only have to do once, right? X minus 2 equal to 0. So x is equal to 2. Our only possible solutions. So there's our proposed solution. Now we look and just make sure that that doesn't cause any problems up here. 2 minus 3, negative 1, that's okay. 2, that's okay. 2 squared is 4 minus 6. 4 minus 6 is negative 2, so we're okay. So the solution is x equal to 2. So it was our proposed solution, and it worked when we went back to the original equation. So remember, whenever dealing with these rational equations, you want to get rid of the denominator. So find the common denominator, and then you can just cross it out once you've put everything with the common denominator, and then just work at it, get a solution. Once you've got your solution, go back to the original rational equation and make sure it doesn't violate 0 in the denominator. So you don't want to end up with a 0 in the denominator. If you do, wipe it out. That's not considered a solution. If that means you come up with no solutions like we did in the previous problem, then fine, the solution is the null set. There is no solution. And I prefer, if it is the null set, that you either put the null set or the empty set. So either the squiggly brackets or the null set, one of those, as opposed to just saying there is no solution. You're right, there is no solution, but it's best to give the solution set as the null set or empty set. Okay, well, this is an applications, other types of equations and applications section that we're working on. So what I want to look at now are rate problems or work rate problems. And work rate problems, I'm just going to grab my paper because it's got some information here that I'm going to want to look at, but just to make sure. So basically, when you have a work rate problem, you're basically saying we're going to call A the job that you're working on, whatever it happens to be. Mowing a lawn, painting a house, washing cars, whatever the case may be. And the work that gets done is equal to the rate times the time. The rate is a ratio of the amount of work done in a certain period of time. If I can mow 5 lawns in 3 hours, then my rate is 5/3. 5 lawns in 3 hours. If I can mow 1 lawn in 2 hours, my rate is 1/2. So basically, you can look at the rate as being 1 over the amount of time it takes to do the job. So R is equal to, you can do one job in this amount of time. So it's basically a specific case of this where we're saying A is 1. You're completing one of something. Now, why do we care about this? Well, there's a number of reasons why we may care about this. We may just want to know how long it's going to take. Okay, if it takes this person, 5 hours to mow a lawn, how long is it going to take them to mow 7 lawns? Or if it takes them 5 hours to mow a lawn, how many lawns are they going to have mowed in 8 hours? If they have an 8-hour workday, how much work are they going to get done? So these are some reasons we do this. Also, we may do this because we are looking at more than one person working together. And I'm sure you've all been involved in some sort of a work project, especially if you have siblings, where you go to do something and you've got one person who's working and they're working really fast. You got another person who works really slow. Then you have somebody else just kind of a medium speed. And you're trying to you may want to figure out, well, if this person's working that fast and that person's working that fast and the other person's working at this other speed, how long is it going to take us to get the job done? Because I may look at it as I can get this job done in 3 hours. Well, Joe can get this job done in 2 hours. If we work together, how long is it going to take us to get this job done? And no, don't just look at it and say, well, if it takes you 3 hours and takes him 2 hours, then it's going to take 2.5 hours, because that's wrong. It's not just the average of them. It's how they relate to another, because you would think that it's going to be the average, but in reality, what's going to happen is I'm working at a certain speed. If we work for 2.5 hours, well, obviously, first of all, we had 2 people working, so that would have to go down 1.25 hours, right? If you say it's half, we're now working at the average speed, but there's 2 of us working at that average speed. So a number of things come into play here. So what I want to do is I want to look at an example. So I'm going to get rid of this rational equations part, but I'm going to leave the rest of that up there. And I'm going to pull up one of my famous PowerPoints. So I'm going to come back into screen here, and we're going to share this slide just so we can see the word problem. So we've got this work rate problem. Lisa and Keith are raking the leaves in their backyard. Working alone, Lisa can rake the leaves in 5 hours, while Keith can rake them in 4 hours. How long would it take them to rake the leaves working together? Okay, similar to what I said, it takes me 3 hours, it takes him 2 hours. How long will it take us to get the job done? Okay, so we looked at it. Now remember, when we're dealing with word problems, we want to start pulling pieces out. Lisa and Keith are raking the leaves in their backyard. Working alone, Lisa can rake the leaves in 5 hours. So the work rate for Lisa is equal to 1 job in 5 hours, while Keith can rake them in 4 hours. So Keith's work rate is 1 job in 4 hours. How long will it take them to rake the leaves working together? Okay. Time combined. Okay, so let me get rid of this slide for you, and we'll get into this. Okay, so I just put Lisa's work rate as 1/5. I put Keith's work rate as 1/4, and we want to know how long is it going to take them to get through the job. Now remember, A is equal to R times T. A is the amount of work done. So I'm going to just say that the amount of work done is 1. We're trying to rake 1 yard. Well, if I was finding out how long it would take Lisa to do that, her rate is 1/5 times T. right? And obviously we said that it would take her 5 hours. If t is 5, 1 times 5 is 5, divided by 5 is 1. So of course, she'll have the job done in 5 hours. But she's not the only person working on it. We also have Keith working on it. And Keith's rate is 1/4. He can do it in 4 hours. But he's going to work for the same amount of time as Lisa. So basically we said we're going to do 1 yard. The amount of time, they're both going to spend the same amount of time, but she can do the job in 5 hours. He can do the job in 4 hours. So she can do 1 yard per 5 hours. He can do 1 yard per 4 hours. And now we just need to solve for t. So if we're solving for t, first thing I want to do is find a common denominator. I see 5 and 4. So I'm going to make that denominator 20. So now I can go through and I can basically just multiply through by 20. So I get 20 is equal to 20 divided by 5 is 4, plus 20 divided by 4 is 5. T. Combine like terms. 20 is equal to 9t. Divide both sides by 9. T is equal to 20 ninths. 20 ninths is equal to 2 and 2 ninths hours. So 2 and 2 ninths hours is how long it's going to take. Well, how much is 2 ninths of an hour? That's a good question. It's 0.22 times 60 minutes. Let me grab a calculator here. $13.2 minutes. So we can do it in approximately 2 hours and 13.2 minutes, the two of them. Whereas it would have taken her 5 hours and it would have taken him 4 hours. Now notice halfway between that would have been 4.5 hours. If you say there's 2 people working at a rate of 1 over 4.5, then you would expect it to be 2.25 or 2.25 hours, which would be 2 hours and 15 minutes. So you see that it's not as simple as just saying, well, what's the average work rate? And then divide by the number of people. It'd be great if it was, but it's not. It actually takes a little less time than that. We actually save another 1.8 minutes by doing this calculation. So that's a work rate problem. And notice that we started with a rational equation to solve. And then we came through, we found the common denominator, multiplied through by the common denominator, which wiped out my denominator and put it into a linear equation. And we just solved for the variable. And then of course we have to look and make sure that it doesn't cause a problem. Well, it does not cause a problem because we don't have any variables in the denominators here. So it's all good and dandy. So there we go. So that's dealing with rational equations and applications.